So as you can see, this is the expression of electric field inside the PN junction diode, and if we try to plot the electric field, this is my E and this is X. Now if we assume this is Xn and this XP minus XP, then the plot of the electric field would be like this, right? So up to 0, this is my origin 0, up to 0 the electric field increases, right, in negative direction and reach a final value, and from that it again decreases up to 0 at Xn, right? Now this is the electric field. Now from this equation and this electric field information, we can also get the value of potential inside the PN junction diode. Now we know that potential and electric field is related by this equation, right? So we can find out the potential by this, right? So it is just this integration that we have to perform. Now we already know the value of E for these two regions, right? Now all we have to do is just put the value of this and find out the value of phi, and by putting the exact boundary conditions we can also find out the integration constant that we are going to face after the integration. Now let us put 1 first, because now we are trying to find out the expression for phi of x between this region, right? Between this region we are trying to find out the potential. So if we put the value, it is, so minus minus gives you a plus, and as all of this has no spatial variable, this would be my expression, right? So it would be NA epsilon S. Now x would give you x square by 2, and this would be xp dot x plus a integration constant, right? Now we cannot use the same condition that we have used for deriving electric field, because you see, electric field, in case of electric field, we saw that electric field before minus xp and minus after xn, it is 0, right? But that the same is not true for the potential as well, because you see, potential and electric field is related by the condition that phi dx is E, right? So E0 means the change is not there, right? That doesn't mean that phi has to be 0. Phi can be a constant that would also give you the same result. So we don't know what is the value of phi before xp. So rather what we can do is that actually what we want to find out the potential difference between this and this, right? And we know that, say we have 2 points A and B, say the potential difference between is 5 volt. That is enough for us, right? We are interested in the potential difference rather than the exact potential of A and B, because it can be 0 and 5, it can be even 1 and 6, But 1 and 6 and 0 and 5, it doesn't matter to us as long as the potential difference between A and B is 5 volt. So if we want only the potential difference between these two, so what we can do, we can assume that at xp the potential is a value which we can assume to be reference, and if you are referencing that, you can say that it is at zero value. So we are taking that reference and we are putting that reference as 0. So my condition now becomes that phi of minus xp would be 0. So this is the condition I am going to put in this equation, and if you do that, the value that you would get is simply C1 dashed is nothing but QNA by twice epsilon s times xp square, right? So this is the value that you would get after putting this equation, this condition, that phi 1 of minus xp is equals to 0. So this is what you get, and if you put this value into this equation, this equation simplifies to this equation simplifies to QNA twice epsilon s x plus xp whole square, right? So this is the expression of phi 1x in this interval, right? So this is only valid for this interval. Fine. Now for uh, for the interval between 0 and xn, we have to change our value of e. So it would be minus of qnd epsilon s x minus xn dx, right? We can even simplify this by d integration. We are just taking the negative sign inside of this expression, and we would have xn minus x dx, right? So if you now do this integration, it would be q n d epsilon s, inside you have xn times x minus x square by 2 plus c2 dashed, fine. So this is my expression, and this is valid between 0 and x of n, right? This is the limitation, this is the region for which this expression will be valid. Now just like in case of p side, that means at xp minus xp, we don't know what is the value of phi. We also, let me change this notation as well. Let us say this is x2, right? Just to distinguish between two potentials. Now, as we don't know what is the potential before xp, we also don't know what is the potential after xp, because the information from which we derive this equation, that is the electric field, it was only valid between xp and xn. So we don't know what is after this, right? So we cannot put that value to find out C2 dashed, right? But one condition that we do have is this potential also have to be continuous within the p-n junction diode, right? That would mean phi 1 of 0 at the origin must be equals to phi 2 of 0, right? If you put this condition into phi 2 as well as in phi 1, what you would finally have, let me erase all this and give you the final result. Finally, what you would have is C2 dashed is equals to C2 dash is equals to Q times Na by epsilon S times N, sorry, it is not Na, this is XP square, right? Oh, also there is a twice, right? So this is the value of C2 dashed. Now if you put this C2 dashed value, in the expression of x2, phi 2 dashed, phi 2x, in the expression of phi 2x, the final value that you would get phi 2 of x is q nd epsilon s into xn into x minus x square by 2 plus q times Na by twice epsilon s xp whole square. Let me check. Yeah, this is the expression. This is the final expression of phi 2 of x, right? Now we know also that at x equals to xn, this phi 2 xn is nothing but VBI. That is the potential, barrier potential. So potential difference, right? So now this potential difference, if you try to find out what would be the potential difference, VBI is nothing but Q by epsilon S. This is 2 Q by twice epsilon S nd xn square plus Na xp square. So this is the value of VBI, right? Now if you put you have another very important expression, that is Na xp equals to nd xn, right? This is another very important result. Now from this, if you put xp into this, you would get the value of xn, and similarly you can find out the value of xp as well, and the depletion width W would be xp plus xn, right? And the value, let me erase this, then it will be easier for me to write and easier for you to see the result. The final value of W is twice epsilon S VBI divided by Q into Na nd the whole thing is in root over, right? This is the value of depletion width for a given doping profile. Fine. And one last thing is that I have showed you the so this is your minus xp, this is your xn. Fine. So your electric field varies like this, okay? and your potential would vary like, so this is your VBI, right? At Xn becomes VBI, right? That's all. If you have any question, you can ask me.